Hey everyone, this is Lakshmikant Tiwari from KGP Talkie. Today we are going to test our Qwen 3.8 Meta's Muse Glimmer model and Gemma 4 model. We will be doing here consistency test. Let me quickly tell you what is the consistency test. As you know, all large language models are a probabilistic model. That means they are not designed to predict exact word on a multiple runs. Basically, they are designed to predict the next token based on some probability. There is no predefined set of the sequence for the next token. That means they are probabilistic model. So in probabilistic model, what happens? There is a very high chance that if you ask the same question again and again with your large language model, then it might not be able to reproduce the same result if you keep asking the same question multiple times. So that is something which we are going to test in this particular lesson. I have taken Qwen 3.8 model, I have taken the Meta's Muse Glimmer model and the Gemma 4 model, and all of these testing is being done on RTX 5090. This is a consumer grade local GPU which I have currently. It is a 32 GB GPU. That means I can easily fit all these models one by one in my GPU. So first of all, let me tell you what current setup I have here with me so that you can aware that what we are actually currently testing. As I told you earlier, I have here RTX 5090. I'll be running here Ollama. Apart from Ollama, I'll be also running here llama.cpp as well for the Meta's Muse Glimmer model so that we can utilize the DFlash of a Muse Glimmer. DFlash technique in Meta's Muse Glimmer model is used to speed up its generation speed. Otherwise, generally, Meta's Muse Glimmer generation speed is like 70 to 80 token per second. But if we use the DFlash technology there, then its generation speed goes beyond the 150 to 200 token depending on the content type. So that is something which we'll be also seeing in this particular lesson. Okay, so let me just quickly tell you exact setup which currently I'm using. So as I told you here, I am using Qwen 3.8, I'm using Meta's Muse Glimmer model and the Gemma 4 model. All of these models, you will notice, all of these models are taking generally 17 to 18 GB of the memory, that's the VRAM. Apart from that, here is the additional, the setup which I'm currently using, RTX 5090. This is my current NVIDIA driver version. So I'm sharing all these because if someone want to reproduce the same result, they can also reproduce the same result. And also I used this Ollama version. And apart from that, I use the Q4KM, the KML quantization. This is basically the 4-bit quantization. And I use the only 8000 context window for each run so that I can match performance of various models together. Basically, I can compare the models. Apart from that, you will notice here, each question got repeated 10 times. All right. That is why I said earlier that here we are going to test consistency at 10. That means a single question got repeated 10 times and then we are testing the result of those, the 10 runs. And then we are checking here whether the final results are consistent or not. So what kind of a question we have here? So we have a question related to the accounting. So basically accounts payable ledgers are there. So the questions are like this here generally. There are 12 questions totally and all questions are related to the account payable ledger only. And these questions got repeated 10 times in a single model and then answer actually got calculated. Basically answer is compared with all the previous runs together and then we measured the consistency. For example, if some model is giving the exactly the same result, that means it is consistent. All right. But that doesn't mean that it is accurate. Why? Because let's say if some model is giving us the wrong result, but the wrong result is a consistent. All right. So that means it is consistent in giving the wrong result, but not in the correct result. So this could be, when I say consistency is 100%, that doesn't mean that the model is 100% accurate. So this is something which you need to also understand. So obviously, as we move ahead in this lesson, we'll be discussing those part as well. Okay. Apart from that, as I talked earlier about the, the speed. So generally we have 150 to 200 token per second speed in our Qwen 3.8 and the Gemma 4 model. But if we enable the DFlash technology in the Meta's Muse Glimmer model, then we are also going to get the same level of the generation speed generally as we have there. Okay, so now the question comes here, from where this speed is coming up. Okay, so there is a technology named as the MTP, that is the multi-token prediction. If anyone of you do not know what is the MTP, I have already covered this in my previous lesson where I have really talked about the MTP next token predictions in very detail. But quickly, let me just tell you here. So what happened in MTP actually? In MTP, your model is going to predict the multiple token in one pass. Otherwise, generally what happened, if your model is trying to predict this token, okay, then in general what happened, if model is predicting this token, it predicts only this token. It does not talk anything about the future tokens. But in MTP, what happened, if model is predicting this one, then your model is also working on these tokens as well. So you can say that here the multi-token prediction length is going to be the 3 here, because 3 future tokens are going to be predicted here as well. Okay, now the question comes in here, how many tokens we can predict and so on. So that is something which I have covered in very detail in my previous video. As of now, just try to understand from where this large speed, higher speed is coming up. Higher speed is coming up from the MTP prediction, and by default MTP is selected here for. Okay, cool. Why I'm sharing this? Because before I start giving you, my judgment, not my judgment, basically before I start sharing my result or the testing result, I need to tell you what are the basic configuration which I have used in my benchmarking. Okay, again, these are the configuration which I have used in my benchmarking. If you want to reproduce the result, you can reproduce your result by selecting exactly the same configuration. Now let me just share you how this MTP is going to affect the generation speed. Okay, so generally in Ollama, that MTP is known as like drafting on or off. All right, so this gray one which you are seeing here, this is drafting off, and then this colored one which you are seeing here, when drafting feature in Ollama is enabled. One thing you will notice, it is doing good with the Qwen 3.8 and it is doing good with the Gemma 4 26 billion parameter model. So what is wrong with the Muse Glimmer model? Okay, so what is wrong with the Muse Glimmer model is actually Muse Glimmer does not support drafting on and off or like that in the Ollama. So what Muse Glimmer actually does here, Muse Glimmer have the additional layer that is known as the DFlash, and DFlash is something which is supported in the llama.cpp only. Okay, so currently it is not supported in the Ollama because of, if you notice Muse Glimmer comparison with the Ollama, you will find out Muse Glimmer generation speed is always lesser as compared to the Gemma 4 and the Qwen 3.8. If I want to tell you here in the detail that how it is actually working, one thing you will notice here, Qwen 3.8 have here the MTP prediction enabled. All right, because of that, when MTP is enabled, its speed is really high, whereas Gemma 4 does not have any, the MTP. Even after that, its speed is really high. Then the question comes in here, why it is happening? It is happening because this Gemma 26B, which you are currently seeing here, this is actually, activating only 3 billion parameter model. All right, that means this model have here MOE architecture. That's mean mixture of expert architecture. It has many, the experts there, I guess 128 experts there internally, but it is actually activating only 3 billion parameter. That means while calculating the result, only 3 billion parameters are being used. Because of that, you are seeing here, its speed is really very fast, even without the MTP. Now, I hope it is very much clear why this speed is coming, because of the MTP. All right. And when you will get the better speed in the Muse Glimmer, because of the DFlash technology. And why you are getting the higher result for the Gemma 4 26B, because it is actually using only 3 billion parameter for the result generation, for the token generation. Now let's go ahead and talk about the Meta's Muse Glimmer model a little bit more. As I told you earlier, this Meta's Muse Glimmer model does not have anything related to the draft head inside the Ollama. So what it has actually the DFlash technology. All right. So it is a separate file which need to be downloaded so that you can run it inside the Llama server. Once you download it, then you can just simply run this command here. All right. By the way, the article link is already given in the video description. Then you can just simply run this command, and thereafter you will see your Muse Glimmer model has started generating, the higher token speed basically. All right, great. So the one thing you will also notice here, this generation speed is actually capped by the kind of the GPU you are using. As I'm using currently RTX5090 GPU, so you will notice RTX5090 GPU have roughly around 1.8 terabyte, the per second memory bandwidth. And as per that, if you get the total number of weights and so on, if you do the math, then you are going to get the maximum number of token capping, that is going to be the 107. That means if we do not use the additional technology, then the maximum speed which we can get here on RTX 5090 is 107 token per second. All right. And generally you will notice we always get 70 to 80 token per second generation speed without any kind of additional technology. Without any kind of additional MTP predictions or DFlash technology. That is why you are seeing here Muse Glimmer model is giving us like the 80 token per second speed, that is the 75% of the ceiling, and Qwen 3.8 gives us like 75 to 76 token. This one is coming with the MTP. I'm talking without MTP or without any additional technology. So that is like 70%. So overall you can say here in dense model, you can get like 70 to 80% of the maximum ceiling. All right. So if some technology is coming tomorrow, let's say, if some new model is coming tomorrow and you are trying to find out what is going to be the, the natural speed, the natural speed is going to be the 107 token per second for the model, which is in the range of 30 billion parameter. Okay, great. So as I told you here, this DFlash technology is going to increase the token generation speed, and this is what you can currently see here. So if DFlash is not used, then you are going to get this speed, that is like 70 to 80 token per second. But if DFlash is used with the speculative decoding inside the DFlash, then you are going to see here how generation speed is going to be increased here. So this, what you are currently seeing, this is actually the token per second. That means if DFlash is used with n equal to the 24, then the maximum speed you are going to get here the 252 token per second in Meta's Muse Glimmer. All right. And on average, you are going to get here around 146 token per second. Overall, this thing which you are currently seeing here, this is the content dependent. So for some content, you might get a higher speed, but for some content, you might get the lower speed. Okay, because of that, when you see this speed, what you are currently seeing here in various benchmarking, you will see the different numbers. The different numbers are because the different kind of the problem statement. Because if a particular sequence is very much predictable, then their generation speed is going to be fast. But if sequence is not predictable, then in that case, generation speed is going to be slow. The one thing you will always notice, generation speed is going to be always same. In the same range, irrespective of the content type, if you are not using any kind of additional technology, like if you're not using the MTP or if you're not using the DFlash. Okay, cool. Now I hope it is very much clear to you. Now you have understood how DFlash and MTP is actually increasing the overall generation speed, and you have understood the differences between the Qwen and Meta's Muse Glimmer and the Gemma 4 model. One more thing I also want to tell you here, a lot of people on the internet have been talking about the reasoning. All right, so many people have reported that Qwen 3.8 literally produces a lot of reasoning tokens as compared to the other models. So here I want to tell one thing here. So why this is actually happening? So there are multiple reasons. First of all, this Qwen 3.8 reasoning cannot be controlled by the Ollama. So the people who are using the Ollama, All right, so they might see the higher reasoning. And apart from that, the Ollama automatically inside the model ingest their, ingest this low, medium, high, and low, medium, and high reasoning parameter inside the prompt instead as a parameter. Because of this inconsistency, for example, some people are testing this on Ollama, some people are testing on, the Unsloth, some people are testing it on the llama.cpp, because there are different parameters or configuration settings which actually controls the reasoning. Because of that, you will be seeing a lot of the reasoning variation between the benchmark to benchmark. In my case, you will notice one thing here. If reasoning level low is selected, in that case, we are getting on average this much of the token. For my problem statement, again, I'm telling you, this is accounting related problem statement. But if someone is doing benchmarking on some other problem statement, then their numbers can be different. Okay. So if I set here the medium, then I'm getting this one. And if I set a high, then I'm getting this one. So what are you noticing here? One thing you will notice here, generally they are not changing much. Even if I change here reasoning effort, low, medium, or high, even I see here they are almost the same here. Okay, in the same range. Why it is happening? It is happening because seems like Ollama is not honoring the reasoning, the reasoning level which we select through the API. So that is the reason. Seems like because of that, it is not actually, the honoring that. Okay. Apart from that, one more thing I want to tell you here. There was a case, so I wanted to just report you here. When I was solving a problem statement, there were time when actually Gemma 4 kept thinking, and it ran out of my token budget. Otherwise, you will notice Qwen 3.8 and the Meta's Muse Glimmer model, they were very much under my token limit. That means they were able to perform my result properly without any issue. I mean, they were able to give me the result without any issue. Okay. So now here we come, as we talked earlier, that how consistent it is going to be. So that is something which I have shared here. So the one thing you will notice here, there is a greedy sampler, there is the default sampler. So any of you, if do not know how LLM decoding technique works, let me just quickly tell you what happened. So actually what happened, let's say your LLM is trying to predict this particular token. All right, and all these previous tokens are predicted in the LLM, and it is trying to predict this token. All right, so I'm just writing here the token. So this one it is trying to predict. So what happened actually in practice, your LLM is going to have here so many options. There is not just a single, the token. So it is going to have here the multiple token options here. So there are so many options. How many options there could be? Length of dictionary option. So basically, whatever total number of tokens are there inside the LLM, I'm saying here unique token. So all those tokens are possible here, all right, in the prediction. But how LLM actually select which one is the right one? So actually there is the probability distribution function. So something like this here. So where you have a maximum probability, all right, so that is most likely to be the selected tokens. But generally what we do here, we assign here some range here. Okay. So whatever token fall between these range here. So there could be like 10,000 token, 100 token, or 10 token, whatever falls under a particular range. We generally select randomly one token out of those range. And then we say that, then LLM says that, okay, this is the predicted token. Okay, cool. So that is how this decoding works. Now in the decoding, there are multiple technology there. So let me just write it here. So in decoding, you will see here the greedy one. Okay. So the greedy one means whatever have a maximum probability. All right. So it is just going to select that one. All right. So maximum probability, it is going to select that one. But the other one is going to work on the range of probability. So as I explained you earlier, so it is going to work on the range of the probability. So it can take here the some range. Generally, we say that range as a top P or a top K. So when I say here top P, let's say, so top P, we can say that, okay, select the top 1% of the most possible tokens and then randomly select one token. Or we can say here the top K. So in the top K, what we say here, if top K is, let's say, the 100, then take the 100 most possible token and then randomly select one token. Okay, cool. Now I hope it is very much clear what is greedy sampler and what is the default sampler. Okay, so default sampler, we are not talking about any kind of sampler here. So default sampler is the sampler provided by the model provider itself. So whatever sampler is there by default inside the model file by the provider, that is going to be our default sampler. We don't know what kind of sampler is that. Basically, I'm not disclosing that because anyway, I just took that model for the testing. Okay, so I select this greedy sampler first and then I check here. If I select the greedy sampler, then for Qwen 3.8 and Meta's Muse Glimmer model, I'm able to get the 100% consistent result. Basically, if you remember, we had total 12 problem statement and these problem statement ran 10 times each. That means there is 120 times basically, but this one problem ran 10 times, another problem, second problem runs 10 times and so on. Every time when it is running here for these, they are giving the same result. It doesn't matter how many times you run, every time it runs, it is giving you the same result. That means its result is consistent here. Okay, cool. But if we use the default sampler, again, I'm not naming which kind of sampler was that. So if we use the default sampler, then in Qwen 3.8, we get the 98.3% consistency. That means seems like out of all those 10 run, all right, basically out of all those 10 run, it was not able to reproduce the result 100% time. Okay, whereas you will notice here Meta's Muse Glimmer model was able to reproduce the same result with the greedy sampler and the default sampler provided in the Meta's Muse Glimmer model. So worst was here the Gemma 4 26 billion model. So when we use the default sampler, we get here 93%. So seems like this top K or top P was used in this particular case. Whereas if we use if we use the greedy sampler, then we are getting here 99.2%. Basically, you can see here the result actually. So here 12 out of 12 is being passed here. All right, with the default one here, there is a little bit issue. But again, with the greedy one, 12 out of 12 is being passed here. Again, here in the in Gemma 4, there is some problem. Okay, so now I'm telling you one thing here. So if something is repeating, that doesn't mean answer is correct. For example, let's say if your model is saying 1 plus 1 equal to 3, and every time you run it, it is going to say you 1 plus 1 equal to the 3. All right, so you keep doing it 10 times. All right, so you keep doing it 10 times, every time it gives you here a 3. So you will say that this model is 100% consistent. All right, so this is, I'm saying here, this model is 100% consistent. Okay, but what is going to be the accuracy here? Accuracy is actually 0. Okay, so when I say a model is 100% consistent, that doesn't mean that the model is accurate. So that is something which we are going to see here. Okay, so in this case, actually in the Gemma 4 case and in Qwen 3.8 and Muse Glimmer model, so you will notice apart from this Muse Glimmer model, none of these models are accurate in all of their repeat. So what do you understand here? So like I told you, if model is consistent, that doesn't mean that model is actually accurate. Okay, so the result could be wrong, but wrong result is coming a multiple time. Okay, because of that, you will also see there the accuracy is also low and the consistency is also low if the wrong result is coming multiple time, but a different result. Okay, cool. So the one thing you will notice here, all right, so this wrong result is coming 83% of time, and whereas you will see here 93%. So what does this mean? Let me just quickly tell you here. So this says that a model not consistent, that's the 92%, and then it says that the accuracy is again just 83%. That means the model which is not able to generate the correct output, that model is not consistent. So you can understand here. So basically where model is hallucinating, and if you try to generate the the answer for hallucinated model, then the hallucinated model is going to generate the different answer multiple time. Okay, so this is what it is, this number is currently telling. Apart from that, as I told you here, this is this is the configuration which I selected in the Ollama to run. And then again here you have the top K1. So as I told you here, so top K1 means it is going to be the greedy search. All right, why? Because the maximum, whatever token have a maximum probability, that particular token I just selected that. Okay, cool. So the one thing you will notice here, the problem number 9 was creating a issue in a Gemma 4 26 billion. So this is what I told you here. Earlier we had a 92% of consistency and then 83% of the accuracy. That means this is where model was actually disagreeing with itself. Basically there was a randomness in generating the answer. That means this is where this particular model was suffering. Otherwise, for all other problem statements, it was really doing good. So what was the problem there? The problem was there, this one. Okay, so 9 times it has repeated this, 1 time it has repeated this one. Basically 1 time it has given this answer and 9 times it has given this answer, whereas the correct answer was this one. Okay, so do you see here where model is wrong, their model is actually giving a different result. Okay, that means if a particular model is not able to give you the correct result, then it is very high, it is very high, possibility there that the model might give you a different answer for a different run. Okay, great. So that is what I told you earlier, that we cannot say that if model is 100% consistent, that means the model is 100% accurate. So the problem was happening with the outstanding token, and that problem came with the Gemma 4 26 billion parameter model only. Otherwise, everything was doing good. Okay, great. Now let's just see that how it is doing on the llama.cpp. As I told you earlier, Qwen 3.8 gives us around 173 token per second, whereas if we add the Muse and the DFlash together with the llama.cpp, then it is going to give us like the 278 token per second. This is literally very high speed. This is literally very high speed. Now the question comes in here that does this DFlash is really accurate? So this is where it is really going to be very important. So DFlash gives us very high, the speed, but you will notice here that the DFlash accuracy is actually decreasing. Okay, so the DFlash gives us the speed, but the accuracy is not that much good. Okay, so you will notice here when your token speed is generally 70 to 80 token per second. All right, at that time, Meta's Muse Glimmer was giving us a 100% accurate model. 100% accurate result. But when we set the DFlash, it was giving us a very high speed, like 275 token per second. This is literally very high, but the accuracy was just 75%. Okay. Previously, we had seen the consistency was 100%. Then what is the problem here? So the problem is related to the accuracy, not the consistency. Why? Actually, what happened here, in this case, what the Meta's Muse Glimmer actually did, Meta's Muse Glimmer has actually generated the answer something like this. Okay, so every time it has generated the answer like this value. So for a particular question, if it has given once this result and it just repeated it 10 times. Okay, so if it repeated this 10 times, you are going to see here 100% consistency, but so 100% consistency, whatever its spelling is here, consistency. So 100% consistency, but the accuracy is here 0%. Okay, so this is what I was telling you earlier. Okay, great. Now I hope all of you have understood that if a particular model is 100% consistent, but that doesn't mean that your model is 100% accurate. All right, everyone. So this is all about in this lesson, and I hope you must have really enjoyed this particular lesson. And we have really deep dived here inside the Qwen 3.8 Meta's Muse Glimmer model and the Gemma 4. We had seen its speed and overall the consistency and other stuffs. And if you want me to do the benchmarking on any particular problem statements, please do let me know. I would be more than happy to do that one. And also please do not forget to subscribe this channel and also like this video. All right everyone, bye bye, take care.